Welcome to Akademika Lab Solutions. RFL-MCT-A Microstrip Component Training System designed by Akademika covers the active and passive devices used in the microwave integrated circuits. This system, along with the 3 GHz Spectrum Analyser or an RF Generator and Detector Module, enables the students to characterize active devices like VCO, amplifier, mixer, and pin diode switches. S-parameter measurements of passive devices like coupler, circulator, power divider, and filters can also be measured using this training system. Gain measurement and isolation of an Mmic amplifier. This monolithic amplifier has 4 terminals. Terminal 1 and 3 are the RF input and RF output respectively, and terminal 2 and 4 are grounded. This circuit has 2 DC blocking capacitor at the input and output of the amplifier. It also has a biasing circuit at the output stage of the amplifier. In this experiment, we will measure the gain of the amplifier, that is S21, and the isolation of the amplifier, that is S12. Connect the output of the variable DC power supply using the SMB male connector to the bias terminal of the amplifier. Initially, set it to 0 volts. As shown, we will set the tracking generator of the spectrum analyzer to -20 dBm and apply it to the input port of the amplifier. The output port of the amplifier is connected to the spectrum analyzer. The spectrum analyzer will display the noise floor, which is around -38 dBm. The frequency range of the spectrum analyzer is set from 500 MHz to 1.5 GHz. Now, as you set the DC bias voltage to 3.8 volts, the amplifier will be in the active region of its operation, and now the output of the amplifier is approximately -20 dBm across the band of frequency. When the bias voltage is set to 5 volts, the output is approximately -3 dBm, indicating a gain of 17 dB at 600 MHz. Also investigate the response of the amplifier across the frequency band and analyze the result. Keep on increasing the bias voltage in steps of 0.5 volts up to 7.5 volts. You will see the gain of the amplifier increasing. Plot the graph of bias voltage versus gain. You will see the gain of the amplifier increasing maximum up to 20 dB, after which it will reach saturation. Isolation of the amplifier. Now, we will reverse the connection to the amplifier to measure the isolation, that is S12. Here, we will apply a -20 dBm signal at the output of the amplifier and measure the input port of the amplifier by connecting it to the spectrum analyzer. The signal of the spectrum analyzer shows a reading of -40 dBm at 600 MHz, which indicates that the isolation is around 20 dB at 600 MHz. Investigate the response of the amplifier across the frequency band and analyze the result. Characterization of voltage controlled oscillator. The VCO has a 5 volt VCC terminal with SMB connector, a 0 to 10 volt tuning voltage with SMB connector, and an RF output with SMA connector. Using the SMB connector supplied, connect the output of the variable DC power supply to the VCC terminal and the tuning voltage terminal. Set the VCC terminal to 5 volts. Connect the output of the VCO to the spectrum analyzer and view the results. You will see the frequency spectrum at 1.3 GHz, which is the free running frequency of the VCO. Now, as per the characteristic of the VCO, as you change the tuning voltage from the DC power supply, you will see the frequency shift. Plot the graph of tuning voltage versus frequency. In this way, a VCO can be used to generate different frequency within its band by changing the tuning voltage. Characterization of Rf Mixer. A mixer is a non-linear circuit that creates new frequency from 2 signals applied to it. In our circuit, we have RF input to which a 40 MHz signal is fed from the function generator and a local oscillator input to which 1350 MHz is given from the VCO. The output of the mixer can be seen on the spectrum analyzer, which will be a sum and difference of the local oscillator input. In our case, 1350 minus 40 MHz and 1350 MHz plus 40 MHz. This signal can be viewed on the spectrum analyzer. Characterization of RF pin Spdt switch. Single pole, single throw switch serves in circuits as on-off switches. When the switch is closed, the circuit is on. Using the SMB connector supplied, connect the output of the variable DC power supply to the V bias terminal of the Spdt switch. Initially, set the voltage to 0 volt, indicating the switch is closed. Set the TG output of the spectrum analyzer to 0 dBm and apply this as input to the Spdt switch. The output of the switch can be seen on the spectrum analyzer. Here, you see that when the V bias voltage is 0 volt, the circuit has very low insertion loss, indicating the circuit is on. Now, as we increase the V bias to 5 volts, the pin diode is on and it will break the circuit. The same can be seen on the spectrum analyzer where the insertion loss is very high. Characterization of RF pin Spdt switch. Single pole double throw switch is a switch that has only single input and can connect to and switch between the two outputs. Using the SMB connectors supplied, connect the output of the variable DC power supply to both the V bias terminal of the Spdt switch. Initially, set both the voltage to 0 volts. Set the TG output of the spectrum analyzer to 0 dBm and apply this as input to the Spdt switch. Now, if we apply a 5 volt DC bias voltage to the left terminal of the switch, the signal will be transmitted at the RF output on the left side of the switch. This can be seen on the spectrum analyzer where the insertion loss is very less, and when the 5 volt is applied to the right terminal of the switch, keeping the left terminal at 0 volt, signal will be transmitted on the right side of the switch. In this way, we can divert the signal by applying voltage to the bias terminal. Characterization of pin diode as variable attenuator. This circuit has input and output port with SMA connector and two SMB terminal, one for the bias voltage and the other for the control voltage. Using the SMB connector supplied, connect the output of the variable DC power supply to the bias voltage terminal and the control voltage terminal. Set the bias voltage to 5 volt and control voltage to 0 volts. Set the TG output of the spectrum analyzer to 0 dBm and apply this as input to the RF in of the circuit. The RF output can be seen on the spectrum analyzer, which shows no attenuation across the frequency band when the control voltage is 0 volts. Now, slowly increase the control voltage in steps of 1 volt and you can see the attenuation of the signal increasing with increase in control voltage. Maximum attenuation of minus 20 dB is achieved when the control voltage is 5 volts. This verifies the principle of operation of the pin diode as a variable attenuator. Characterization of Schottky diode detector. The principle of diode detection is rectifying the AC component through a diode and generating voltage as DC component. The detection makes use of the non-linear characteristics of the Schottky diode, hence, a bias circuit is not required. Set the TG output of the spectrum analyzer to minus 25 dBm and frequency is set to 1 GHz. This is given as input to the Schottky diode detector circuit. Connect the digital multimeter across the load resistor. Set the digital multimeter to millivolt DC voltage range and measure the output voltage. Now, vary the input to the Schottky diode detector circuit by changing the TG power from minus 25 dBm to minus 15 dBm in steps of 1 dB and measure the DC voltage on the digital multimeter. You will see that as the power increases, the DC voltage increases. Now, you can plot the graph for input power versus DC voltage. This circuit converts the low level of RF signal to DC voltage. This is used in applications of RF energy harvesting. Determination of bandwidth and quality factor of a microstrip ring resonator. Microstrip ring resonator is a device that exhibits resonance. It has 250 ohm microstrip feed line and a ring. There is a small gap delta between the ring and each feed line. Resonators are mainly used to select specific frequency from a signal. Set the tracking generator output of the spectrum analyzer to 0 dBm. This is given as input to the port 1 of the microstrip ring resonator. Connect port 2 of the microstrip ring resonator to the spectrum analyzer. Set the start frequency on the spectrum analyzer from 1 GHz to 1.5 GHz. The display trace on the spectrum analyzer is the insertion loss, that is S21. Select the markers as shown and turn on the marker table. The Q factor is very high, and this indicates that the ring resonator is having narrow bandwidth. Measurement of transmission and isolation characteristics of circulator. A circulator is a passive, 3-port device that only allows a microwave or radio frequency signal to exit through the port directly after the one it has entered. Set the tracking generator output of the spectrum analyzer to 0 dBm and apply this to port 1 of the circulator. Port 2 of the circulator is given to the spectrum analyzer and port 3 is terminated with 50 ohms. Set the frequency range on the spectrum analyzer from 1 GHz to 3 GHz and set the marker at 2.4 GHz. The display trace on the spectrum analyzer shows the transmission characteristics, that is S21 of the circulator. Similarly, you can measure the transmission characteristics, that is S32 of the circulator, by applying the input at port 2 and measuring the output at port 3 of the circulator. Now, apply the 0 dBm signal from the tracking generator to the port 2 of the circulator. Port 1 of the circulator is connected to the spectrum analyzer and port 3 is terminated with a 50 ohm load. The display trace on the spectrum analyzer shows the isolation characteristics, that is S12 of the circulator. Measurement of power division characteristics of microstrip power divider. A 3 dB power divider splits an input signal into two equal parts. A 3 dB power divider splits an input signal into two equal output signals. This device has a quarter wave transmission line to effect the split power. There is a resistor placed between the two output ports to achieve high isolation between the output ports while maintaining a match on all the ports. Set the tracking generator of the spectrum analyzer to 0 dBm and connect it to port 1 of the power divider. Connect port 3 of the power divider to the spectrum analyzer. Terminate port 2 of the power divider with 50 ohm load. The displayed plot on the spectrum analyzer shows the insertion loss, that is S31, or power division for the signal measured at port 3 and RF input at port 1. Displayed plot shows the insertion loss S31 is around minus 5.4 dB at 1.4 GHz, which include a minus 1.2 dB loss of the RF cables. This means 3.2 dB power is transmitted at port 3, which verifies the design specification. Characterization of microstrip bandpass filter. Set the tracking generator of the spectrum analyzer to 0 dBm and connect to port 1 of the bandpass filter. Connect port 2 of the bandpass filter to the spectrum analyzer. Set the frequency range on the spectrum analyzer accordingly. The display trace on the spectrum analyzer shows the insertion loss, that is S21. Apply markers as shown and note the readings for the display trace. The display trace on the spectrum analyzer shows the insertion loss of the band stop filter. Measurement of coupling factor isolation, directivity of microstrip coupled line directional coupler. Set the tracking generator of the spectrum analyzer to 0 dBm and connect this to port 1 of the directional coupler. Connect port 2 of the directional coupler to the spectrum analyzer. Terminate port 3 and port 4 of the directional coupler with 50 ohm load. The spectrum analyzer plot shows S21, that is insertion loss of the coupled line directional coupler. Insert the marker at frequency 2 GHz. It shows minus 4.2 dB insertion loss. Now, to measure the coupling between port 3 and port 1, terminate port 2 and port 4 with 50 ohm load and measure the output of port 3 on the spectrum analyzer. The plot shows coupling S31 of directional coupler across the frequency band. Now, to measure the isolation of the directional coupler between port 4 and port 1, terminate port 2 and port 3 with 50 ohm load and measure the output of port 4 on the spectrum analyzer. The plot shows isolation S41 of the directional coupler, which is having very high isolation. Now, you can calculate the directivity of the directional coupler using the formula. Directivity in dB is equal to isolation S41 minus coupling S31.